really very pleased to be here today. And when I came, I had no idea what the symposium was like and would be like. And maybe my talk isn't exactly what I would have done had I heard this morning. However, I will improvise a little bit. I'm going to talk about Rosalind Franklin. She was born in 1920. I was born in 1930. So she's exactly 10 years older than me. In 1958, when she passed away, that was the year I got my PhD. So even though there's only a 10-year difference, you have to understand her career was all finished when I started. So this is really quite interesting. We also overlapped because when I really started out in my first venture in physics, which was at Cambridge University in the UK. So I was an undergraduate at Hunter College to be a school teacher. So when I started, I wasn't planning or even thinking or didn't even know about a career in physics. So this happened, but on the way, I met Rosalind Yallow when I was an undergraduate, and she was teaching at Hunter College for one semester, and there's somebody in the audience here that intersected with Rosalind Yallow, so that we even have a connection there. But she encouraged me to go into science. She said, science really is, you're meant to do that, not to be an elementary school teacher. I think I would have enjoyed being an elementary school teacher, but that isn't what it turned out to be. So anyhow, I wound up at Cambridge University, and I was a Fulbright. And it was there that I said, yeah, maybe this is something I want to do. And so then I spent a year at Harvard, then wound up at the University of Chicago, where I did my PhD. Now, we heard a lot about women in science, so I can speak a little bit about Chicago, because that was the place that I really found out about women in science and women not in science. So, of course, as you heard, in the field of physics, there are really very few women. When I got my PhD in '58, so that's the end of Rosalind's lifetime, we were only up to 2% of PhDs in physics. So you could imagine I didn't see other women, and I would say almost in my whole career I've worked with men, and maybe Jane has been like that too, pretty much, because in our field we don't just, in astronomy there are a few more than in the kind of physics I do. So I have taught all male classes, and I've done all of these things, and so my attitude the whole time is if I get into a situation where I'm not appreciated, I sort of back out gently, and I don't pay much attention to it, and I find places where I am accepted. So when I was a graduate student, there was one faculty advisor that that was available in condensed matter, just one, and he didn't believe that women should be in science. And every time he saw me, he said that to me. What are you doing here? So I got lost, and I never saw him, and he didn't know what I was doing my PhD thesis until 1 month before I defended my thesis. He didn't even know the topic I was working on. So you could imagine how much help I got from him. But at the University of Chicago, there was one person that I did learn something from. That was Clyde Hutchison. He put up with me, and he used to invite me to a Saturday lunch group that he had in his research group, which was in the chemistry department. So, you know, I became a little bit interdisciplinary that way, and I found somebody that would listen to me. But he wasn't on my thesis committee or anything like that. So that was the way that was. And later on in life, you know, you find people that don't appreciate you. They don't think women should be in science, and you just ignore them. So that's what I did. And I work fine with men. And so I've always been in a man's environment. And I don't think about it. I just accept it. I don't think about it. I do my thing. They give me a hard time. I go elsewhere. And that's it. I think Florence knows me. I manage somehow to survive. So, but it was interesting to hear what other people had to say about it, because I haven't really been thinking that much about being female or not. Just I'm concerned about doing my job and trying to do it well. And I also tell my students that that's the way we operate, whether they're male or female. I don't pay attention to them. Okay, so now having said that, we'll get back to Rosalind Franklin. And this is a very telling picture. It's a cartoon that's taken from a website on Rosalind that we found. And so you'll see here, this is her doing the work. And there's Watson and Crick. I guess that must be Watson and Crick there. And we overlapped at Cambridge when I was on Fulbright. And I even heard talks by these people. So, yes, is something the matter with the recording? What? Take a more. Well, no. I'm just talking about this one. I plan to do it on the remote. I haven't planned. I'm just talking about this. This is Rosalind Franklin, a subject of my talk, I thought. So I'm starting there. So I wanted to make some comments about Rosalind Franklin, because I started out saying that we sort of overlap, but we didn't overlap. We didn't know each other, but we could have known each other. And my work has actually intersected with her work. So she came up, and I'll tell you how she comes up in my research. So we did overlap, and I brought that into my talk. So that I will move the slides to show you that. Okay, so, but this is to show what her career was like, and I think it captures the person that did the work and the person that got the credit, and they're not the same. And I think that that's what the society talks about. I didn't hear so much about that today, but I heard some. So now, here she is, and that's a picture of her. She was really a lovely looking lady, and that's her x-ray, and that's her working, and so you could see something about her. I didn't see this, but probably you had this yesterday, so I missed that. And I brought something about a letter she wrote to her father. It's an excerpt that was a guiding thing. You frequently state in your letter, and that's Rosalind writing a letter to her father. And she said, you frequently state in your letter, that's what he says to her, that I have developed a completely one-sided outlook and look at everything and think of everything in terms of science. Well, I think most scientists are like that. We don't think of everything in terms of science, but we think about it quite a lot. Obviously, my method of thought and reasoning is influenced by a scientific training. If that were not so, my scientific training will have been a waste and a failure. But you look at science, or at least talk as if you do, as some sort of demoralizing invention of man, something apart from real life, and which must be cautiously guarded and kept separate from everyday existence. But science and everyday life cannot and should not be separated. And I agree with that. Science, for me, gives a partial explanation of life. Insofar as it goes, it is based on fact, experience, and experiment. In my view, all that is necessary for faith is the belief that by doing our best, we shall come nearer to success, and that success in our aims, the improvement of the lot of mankind, present and future, is worth attaining. I think that most of the people in this room working in science will agree with much of what is said here. But as we also said in the introduction, there's more to life than just science for most of us. And we can enjoy our family, we can enjoy other things that we do. And so I have benefited, enjoyed science, but that's not the only thing in my life. But what I'm going to talk about today is about a little bit Rosalind Franklin and the science that I do in some context. So let's see. So about her, she's 10 years older than me, I told you that already. And she faced an unfriendly and unfair environment. I guess you heard a lot about that yesterday. And the society, I guess, discusses that. I probably don't have to say more about that at this point. So now I'm 10 years younger, and I had maybe a different opportunity to find some people that would listen to me. And in my early years as a graduate student, I studied with Enrico Fermi before he died. He was a really great scientist, and he appreciated women. There was no problem with him with women. There were many other faculty members that had problems, but he had no problem. And so that taught me that you could find people that will talk to you and be helpful. And I use that as a kind of a guiding light. So my own environment was different from hers because I did find people that were friendly and useful. And then I had some other things that happened. Sputnik happened in 1957. Sputnik opened the opportunities for women at that time. It opened opportunities for everybody. Science became big. It was very dormant when I was a graduate student. But then as I was finishing my PhD, all of a sudden, pop, we had Sputnik just at the right time. 58 is when I finished my PhD. And at that time, all of a sudden in the US, they were looking for people that had scientific training. Well, I had scientific training. I just happened to be female. But because I had scientific training, I could be appreciated and get a job. I spent 2 years as a postdoc at Cornell. I got married in 1958, and my husband was working at Cornell, so I was there. The situation there was so unfriendly. They didn't even allow me to work for nothing. They told me we didn't want women around in the lab. So we both moved on. And he was willing to give up his position on the faculty and move with me. He was an assistant professor. He thought he'd have other opportunities, so we moved on. And there were two places at that time that allowed, they would hire people in the same family. One of them was MIT, and the other one was IBM Watson Lab. So we had offers from both of them, but they were really good places, and it was hard to make a decision. But I liked the academic environment, and so did he. So that's where we went. So we went, and that's how I wound up in the MIT family, and I'm still there. So that explains my career. I was encouraged to do science, and I found a place where I could do it. And in that sense, I've had a very normal career, even though I was female. I found that at MIT, maybe not everybody was supportive of women, but there were a lot of people supportive at very high levels, like the president of the university and that sort of thing. And that sets the pace. In 1970, Jerry Wiesner became president, and his wife was very, very active. And she was very influential on him, too, to be supportive of women. And they gave me lots of jobs to do around MIT to promote women, develop careers for them and whatnot. So I felt I was useful. I'm just mentioning that because that's sort of the topic. So not only are we can be do the functions of males in the classroom, but we can have other functions in helping young women in their development. So that's what I wanted to say about that. Okay, so in my talk, I wanted to talk about, I realized that this would be a very broad audience, and unlike what Jane has to say, which is kind of easy to understand by, well, the way she made it anyway was easy for people not working in the field to understand what she's doing. In my situation, it's different because we get down to the nitty-gritty. It's not so hard, not so easy to explain. So I'm going to talk about the broader context of my career because I thought that was more interesting for you. And it isn't exactly what Rosalind Franklin did, but she was trying to reach out also in her statement. She says she was talking about all of science, not only her own niche. So what I've had to do, opportunities to do, I've gotten into, I mentioned after I became lab director at MIT, you gain a certain amount of visibility. So I had many national responsibilities. So I've been treasurer of the National Academy of Sciences, so I managed money even. So we have big budget at the National Academy. So I learned about financial matters, but I learned about financial matters long before that. Anyhow, being on boards of companies and stuff is how you pick all of that up. And if you're in practical sciences like condensed matter physics, I just had many invitations to be on boards. I had no time to be on so many boards as I had invitations. So you gain a certain amount of visibility. And so my advice to the young people that are here, when that happens to you, take it seriously because you learn something. Everything you do, you learn something that you use somewhere for something. And just run with it and have a good time. So this is one of my most recent activities at the National Academy. They asked me to chair the decadal study in physics in condensed matter physics for this decade. So I thought that would be something interesting to tell you what people are working on nowadays. So these are the 6 things that we identified. And one of them is Nano Science, which is what I got the prize for. So I tell you how that all goes together. So the first one is how do complex phenomena emerge from simple ingredients. And what that means is if you take a whole ensemble of electrons, it behaves very differently from the individual electron because the electrons talk to each other and they interact so that their behavior is different. The second is, what is the physics of life? In living systems, there's something that happens that's different from non-living systems. Well, we heard about DNA replicating. Maybe the life process has something to do with making all of that happen. And inanimate things, even if they happen to have DNA, don't do the replication. But some of the biology people in this room, the geneticists, can explain that to me, why that is. But there's a physical understanding behind that could be quite important. And that's what a whole branch of physics is devoting themselves to. And this is a very far growing field. And I'm not connected with the Kavli Foundation, but I have been connected with the Packard Foundation for about 25 years. And I've been involved with the giving of the faculty fellowships to young faculty members. They give approximately 20 a year, and it's a 5-year period. And they get a handsome amount of money to do their research when they get these awards. So in doing that, I got to know David Packard. He used to sit next to me all the time because I was the only female member on the committee. And I was in that function for almost 20 years before we got the next female member. But as I said, I don't pay attention to the sex of the people, you know, on the committees I work at. You know, we just do it together. I go moving down this list here. What happens far from equilibrium and why? So we have different phenomena. I'll show you some examples of that. Out of equilibrium is very interesting because out of equilibrium situations behave very differently from equilibrium. Like a storm is very different from the nice weather that you have now, with this air motion happening and whatnot. So the next one is energy demands of the future. How will we? That's one of the big challenges of this decade. Young people are moving into that research field in large numbers now. I see that in the applicants, the talented applicants, what they're doing. The fifth one is about information technology. That explosion has been going on my whole career. It started when I was very young. And so now we're down now to very, very small length scales. And we can't get closer than the size of a molecule, I don't think. So we have single molecule devices now in electronics, but I don't imagine we'll have single atom devices very soon. So we're not going to get much smaller than what we are now. And what discoveries in the nano world, and that was kind of what my prize was about. So maybe you'll hear a little bit more about it. So this is a little bit what happens out of equilibrium. You can't see very much what the pictures are, but I'll tell you what they are. This is a swarm of fish. You have a single fish swimming. It swims very differently from a whole collection. They swim in some kind of, you go to this aquarium, you can see what they do. They're strongly coupled. In other words, they do their motions. And so here's a galactic system here. And the galaxies themselves, they have a form. It's not a distribution of stars out there that's just uniform, but this is what happens in nature, and the behavior of galaxies is very different from the individual stars. Some of the astronomers in the room can tell us more about than I can. But these studies are important, and we have to start thinking about them. So the out of equilibrium can make new materials like glassy alloys, polymers, and all kind of interesting things. But they could also break objects apart, like this airplane. And we like to have these things, the good things, but we don't like to have the bad things. And we have to learn how to control them. That's what that's about. Information revolution, I already said that we're down to single molecules. And there are devices now based on single molecules. They don't work all that well yet, but you'll be seeing that happening in the next decade. So this is the energy revolution. You can't see very much because the room is way too much lit up. But you can see here, United States is all lit up. Japan is lit up, and Western Europe. But there's Africa out here. You could hardly see Africa. And in South America, you can only see in little bits. So you could see that the industrialization of the world is very non-uniform. And we're going to see a little bit more change in that. But it's going to be a long time before the whole world catches up. Or maybe we don't want it to catch up. Or maybe they don't want to catch up. Maybe they're happy the way they are. Maybe we shouldn't interfere with them too much. That's not my call. No. And the energy demands, so these are new devices, and you can see that a number of these devices involve nano stuff, and it's the nano stuff on the energy demands that I've been working on. That wasn't my Kavli prize so much, but it was a little piece of it. This has to do with my phonon work that was mentioned in the prize. And so we're down to the nano scale with new materials made at the nano scale and manipulation of new materials. And that's been what I've been involved with for the last 50 years, mostly, in one form or another. So now this didn't quite make the whole screen, but there's a scale here that shows you that this is carbon science, and this is publications in the field. It's too bad that you can't see this view graph because this is an important one. Okay, thank you. That's good enough. You can just keep it that way. They can see it well enough. Okay, well, that's better. Okay, just leave it like that. Just any form, then we'll go back, okay? Oops, I want to go back here. I want to go back. No, okay. Okay, here we are, close enough. Let's not mess too much, because I want to finish this talk without too much ado. So in 1947, oh gosh, how do we get back to the? Yeah, maybe you. Can I work from there?
Right here.
Okay, I'll say next slide, Florence, and you give me next slide. So my entry into the nano world, I was going to say a little bit that happened before my entry into the nano world. So 1947 was the first paper on carbon systems. And it was for one-dimensional assembly of carbon atoms. And it was paper on a monolayer graphene. 1947. It was rediscovered, got the Nobel Prize in 2004, but the original paper is 1947, and that's what got me into this field, that paper. So Rosalind Franklin, she's between that paper of 1947 and my entry into the field, which is 1960, and somewhere buried in there is 1960 to 1970. But what I was going to show you is I have one slide from each decade, pretty much, to make it fast forward. So in 1947, for me, Nano Science started. One layer of graphene. That was the first paper that I know of that had low-dimensional physics. And after that was the work of Rosalind Franklin, and her papers were in the early 1950s, pretty much when I was at Cambridge and getting my own PhD. Because, as I said, she died when I completed my PhD. And my PhD was on superconductivity. It was on a totally different area. I didn't really intersect with Rosalind Franklin at all. And so when I got my first position in 1960, I was told that you can work on anything you want, but don't work on anything you know something about. So I had to switch fields entirely, and it was then that I started working on high magnetic fields. And so I'll take you through my story. So the first decade with high magnetic fields, we were working on the electronic structure of graphite, three-dimensional. And if you take a single layer of that, you have graphene, and that's the nano thing I work on now. So I've kind of come a complete route, because I started with one layer, because that was my model, and we had a theory for that. Somebody said that it's good to have a theory. Remember, I think that was Jane Liu that said it's good to have a theory. So, okay, so that's where I started. And so we developed understanding, experiment and theory both, for graphite in the 60s. So then I had the idea that maybe we could I knew about the paper of 1947. And also, I knew of Rosalind Franklin's work that there was a structure. So what happens when you have just a single layer? So in 1973, we did our first paper to understand what happens when you make a single layer. But we could only make it, in the 1970s, we could only make a layer by putting something between the other layers. That's the only technology that we had. So we made these intercalation compounds, and we studied the layers of the carbon. So that's single layers of carbon, that's like graphene. And between them, we had molecules separating them. And we could study the carbon layers and what was in between them and how they modified each other. So all of that, this is a large amount of work because you can put many, many hundreds of things between the layers. Then we studied the many things that you could put, molecules and this and that. And so that was the work up till the mid-'80s in my group. So moving on. The next thing was we tried to see what happened. We were doing laser experiments in studying the electronic structure of graphene. And then we had the idea, suppose you just take a carbon surface and you have a more intense pulse of light coming in. Oh, okay. We're going to move very fast forward then. I was told 5 minutes. Okay, so light comes in and it ablates something from the surface. So what comes off? We thought C2, C3, but it wasn't C2, C3, it was something really big that was coming off. And we knew that because if you take a rod and you measure how many atoms are coming off from the end, you could see that it was big chunks. And we figured it was about C100. And in the quest of looking for this, I gave some talks at Exxon where they were doing clusters, and I encouraged them they went up to 15, and I encouraged them to go to higher, because I said we needed C100 somewhere in here. So they did the spectrum, they found all of this new stuff, and this is the beginning of fullerenes. So I'm not going to say much about fullerenes. We didn't discover the fullerenes, we discovered the chunks and got people to measure what was happening, and then the people that identified the fullerenes, in fact, were Kroto, Smalley, and Curl. We didn't do that. Let's move on. So we did spectroscopy. So this is the work we were doing in the 90s now on spectroscopy of the fullerenes. Simultaneously with that, we were studying carbon fibers because the things that came off the carbon surface were something, and we wanted to know more about them. And there was a conference on these intercalation compounds where I met the master of who made carbon fibers, and we started a collaboration. The collaboration turned into a book, in fact, more than one book. And but we were doing fibers, and fibers are long, skinny things like this. We had a conference in Washington where Smalley came and talked about fullerenes, and I was talking about these carbon fibers, these long, skinny things. And somebody asked the wonderful question, it was a very important question. What's the connection between your work out with the carbon fibers and fullerenes? Asked the two of us. They put us on the stage and asked us, what's the connection? The obvious connection was this thing. You can get bigger, make the elongate. We knew you could make C70, so let's make C80 and then get something like this. Okay, so that made us say, okay, if you can do this, what would the properties be? And so we wrote a theoretical paper in 1992 that said, if you could make this thing, we had no idea how to make it, but if you could make it, it would have the properties that these fibers could be either semiconducting or metallic. Well, at that time, nobody had an idea that you could make any object that, just depending on the geometry of how the atoms were on the sheet, would have such highly different properties. And in fact, every time we talked about our model, people would say, oh, that's impossible. But then we did some experiments, and other people did the same experiment, different, related experiments, and we showed that it was correct. And that was the beginning of nanotubes. So that's how nanotubes got started, and this is a spectroscopy of nanotubes. And I'll move quickly through it. You can see that the lines are very big, very, very intense. They differ according to the excitation energy. Anybody who knows Raman spectroscopy knows that that's a resonance effect. We heard a resonance effect from Jane Liu. We have resonance effects here. And they amplify signals by many orders of magnitude. So that gave us an idea. Well, let's look at just one individual nanotube, 1 nanometer in diameter. Nobody thought you could do anything like that, but because of this enhancement effect with resonance, we had a multiplication of many orders of magnitude, and we could see an individual tube. And not only could we tell whether it was metallic or semiconducting, we could tell exactly the orientation of the hexagons just from theoretical considerations. So that really moved this field forward and started the field of single molecule or single nanotube. It started with single nanotube and then went to single molecule spectroscopy. So this is so this has led to now we're doing this thing. We have two of them. Okay, I will finish. So with two of them, you can move up this way. So it's like taking two sheets of paper because they have different chiralities and you can mix and match any way you want. And so we have some theoretical, we can make samples. We can make single wall, double wall samples, triple wall samples, and we can make ribbons. And this is my 1 minute. We're working on all of those problems nowadays. And so we have different edges. You notice that that is a zigzag edge, and this one is an armchair edge. They look different. And you can make in-betweens also. And they all have different properties, and we're studying these. They have remarkably different properties on the nanoscale, because this is now just 1 nanometer in width. So Nano Science is really very interesting because you can do all kinds of things. And this is spectroscopic signals, and you could see that the spectroscopic signals for, say, this is a symmetry forbidden transition. These are the ones that really, you can predict that this sort of thing happens. So this is also theory and experiment together. Another thing that we're doing here is we make these edges. So this is just a ribbon, and so this is where the Kavli prize comes in. This is combining what the phonons do, the excitations of putting light in to create vibrations, and the vibrations heat up the sample so much that we can go from a very disordered system to one that looks like this, atomically organized. And so we made this in the last couple of years, and we're studying this kind of transformation. Now what this is doing, this is the end of my talk, and has to do with the Kavli prize, is that up till now we've been studying two fields in my group for the last 20 years for sure. We studied spectroscopy with carbon systems. And then I got into another project of energy conversion, thermal energy conversion on behalf of the government, because they needed thermoelectrics for submarines and other things in the Navy. So we started working on that system, but that got me into studying phonons. And so we've written many papers on lattice vibrations and their development with carbon systems and many other systems. But one thing that we've been able to do that's interesting, that's the work that the Kavli Prize, I hope there's somebody from Kavli here that can hear, that Kavli has made me enter a new field. Because in the citation of the award, it said that electrons and phonons and their interaction. Yes, we've done some work on the interaction, but it's been sort of passive interaction. Now we're doing dynamic interaction and trying to make totally new materials through this interaction. So, and this is the future work. I think Kavli Foundation likes to make something future. So take two nanotubes like this, and then we have an array of them, like 100 of them. And we send current through, so we make them all hot. And they join and make a bigger tube. So that's the beginning of it. But I want to tell you some more. Let me see if I can go back. What we've seen recently, but this is not published work, is that we not only can make a bigger tube, but we can make a tube that has inner and outer wall. So we get these together, and then when they join, we have one small one and one bigger, and they wrap around. And we're trying to understand how that could possibly happen. That's a totally new phenomenon. And that's future work. So that's the part of the Kavli Prize that I didn't earn yet, that we're working on, and it's inspired me to start a kind of a new field. So you're the first people that I've heard about that we can actually make multi-wall tubes from stacking up individual tubes and getting the phonons excited So we make an electronic transition. That's kind of an interesting new effect. So thank you to Kavli. And this is a picture. I don't know if you can see it very well, but you see Jane Lewis right here. Here she is. And there's me. And there's Fred Kavli, and here's the king who gave us the awards. So that's my talk.